Next we will study about third harmonic addition in sine triangle PWM. The objective of adding a third harmonic into the sine triangle PWM is to increase the DC bus voltage utilization of the converter. So, you can see here there is a 3-phase converter drawn here, and for with sine triangle PWM or with sinusoidal PWM, we get a certain value of load voltage given a certain value of DC bus voltage. With the help of third harmonic addition in the modulating waveform, we can get more AC voltage across the load from the same DC bus. So, this is the main purpose of adding the third harmonic. We get more AC voltage on the load from the same DC bus as compared to sinusoidal PWM. So, we will see then how can we do this. Okay. What is the way of adding the third harmonic? So, before we proceed, I should clarify that in sinusoidal PWM we have seen earlier that the peak voltage that we can get is m times Vd by 2, and with square wave mode of operation we can get 1.27 times this value. So, in linear modulation we get, suppose if we get 1 per unit of voltage, in square wave we can get 27% more than that. Then why do not we go into square wave, or even why do not we go into over modulation? So, between 1 and 1.27 is the over modulation region. So, why do not we go there? Primarily because this over modulation or square wave mode of operation generates a lot of unwanted low frequency harmonics. So, we try to avoid the going into over modulation region. So, it is a natural question, is that what is the cost of it, that we lose this region between 1 and 1.27, because square wave gives us the maximum voltage. So, the question is, can we get more voltage out of the converter? So, this is the basic question, can we get more voltage out of the converter? In fact, it is yes, we can get by adding the third harmonic, and we can get up to 1.15. So, 15% more than the sine triangle PWM. So, how we do it is what we will now study. So, we will first see how we do the sine PWM. So, here we have the sinusoidal modulating waveform and we have a high frequency carrier wave, right. So, the here we see that if m is 0, the sine wave is having 0 amplitude, whereas if m equal to 1. So, if this the height of the triangle wave is between +1 and -1. So, when the sine wave reaches the value of 1, then it touches the carrier wave, beyond which we go into over modulation, below which we are into the linear modulation range. So, if I can draw the sine wave once more, and I can draw this peak of the sine wave, then I can say this is +1 and -1, and if this is theta, then we know that at theta equal to 90 degree and theta equal to 270 degrees, we get the magnitude of the sine wave becomes 1 or -1. Now, if you analyze this carefully, you will see that as the amplitude of the sine wave increases and when it becomes equal to 1, the sine wave touches this +1 and -1, the ceiling +1 and -1 heights only at theta equal to 90 degree and theta equal to 270 degrees. So, but for other regions, for other points, for example, here or here, in these regions the sine wave is much below than the plus 1 or minus 1. So, only because the sine wave is touching the plus 1 at a particular theta equal to 90 degree, we say that we have reached the end of the linear modulation range, and we then stop increasing the sine wave any further, because we do not want to have the unwanted lower order harmonics. But this is a very disadvantageous situation, because only at one or only at theta equal to 90 and theta equal to 270 we touch the waveform, we touch the upper and lower barriers, and then we stop increasing the sine wave any further. Now, therefore, what is the alternative solution? If somehow we can the sine wave down, for example, if we can push this part down and if we can push this part up some way, by some way if we can push this down and that part up, then it may be possible to keep the sine wave within the plus 1 and minus 1 region. Okay, then we are still in the linear modulation region. Now, how can we do that? We can do that by adding another waveform. We can add another waveform to the original sine wave or to the original sinusoidal modulating waveform. So, this another waveform we will see is the third harmonic that we are going to add. Now, why third harmonic? Why not any other harmonic? So, let us see if what will happen if we try to add any harmonic. Before we go into that, we must first try to see the equivalent circuit of this converter. Okay, so, we have a 3-phase converter, and this is consisting of 3 half bridges. VAO, VBO, VCO are the voltage produced by this converter. So, what is the equivalent circuit? The equivalent circuit of this converter is something like this. So, this is the point A, B and C, and this is the O and this is the N. So, this is the load here and this side is the converter. So, this here is the converter, this is the converter equivalent circuit, and this is the load side, the right hand side is the load. So, this voltage here is VAO, and similarly VBO and VCO. Now, when we add any voltage to VAO, or when we add, so when we said that we will add some voltage to the original sine wave, we will add some voltage to the original sine wave, so as to push this point down and that point up. Okay, we are trying to push the point down. Now, whatever extra modulating wave we are going to add, remember that must be a common mode voltage. Okay, it must be a common mode voltage. Why it should be a common mode voltage? Because if we add suppose I add a common mode voltage, so we are generating this additional voltage here. So, we say VCM, that is the common mode voltage. Okay. So, we are adding the common mode voltage, the same voltage to all the 3 phases. It must be done because the common mode voltage, even if you add to the original VAO waveform. So, this is the VAO modulating waveform, okay, VAO reference waveform, and to which we are going to add a common mode voltage. Now, why it is a common mode voltage? Because in the line the common mode voltage will vanish, and hence across the load there will not be any common mode voltage, right. So, because suppose we have added VCM as a common mode voltage to VAO, VBO, VCO. So, then we can see that suppose this is VBO, then the line voltage VAB will be equal to VAO plus VCM minus VBO plus VCM, and hence you can see that the common mode voltage cancels out. So, whatever we are going to add here in this sine wave, so as to push the theta, so as to push the sine wave down here and up here, it must be a common mode voltage, so that it does not appear in the line, and if it does not appear in the line, it will not appear across the load, because the point N and O will be isolated. This is isolated. So, no current can flow between the point N and O. So, this voltage V common mode, so what can we add to this voltage so as to push the sine wave up and down. So, let us start with the first option. So, we can start say by saying that okay, we add this voltage, okay, because we want to push this part of the sine wave, we want to push this part of the sine wave down and this part of the sine wave up. So, this waveform which we have added is a same frequency waveform, fundamental waveform. However, you can understand that although this waveform here, whatever we have added, will push down the A phase waveform, it is true, it will push it down from its peak, but for the other 2 phases, B phase and C phase, which are somewhere here and here, this voltage, this VCM is going to push them up. So, although we can push the A phase down, we will be pushing the B and C phases up and beyond their +1 and -1 limits, which is not acceptable, because they will go into over-modulation region. So, adding this VCM as the fundamental is not allowed. So, this will not be possible to do. So, let us see the second option. So, again we have the sine wave here and we want to push this down and down. Let us add a second harmonic. So, how does the second harmonic look like? So, we can add a second harmonic like this. Right, we can add a second harmonic like this, but you see here the second harmonic is not helping us in pushing the peak down or this lower peak up, because its zero crossing is at the same place. So, second harmonic addition is not possible. Now, next we add the third harmonic. So, this is our fundamental voltage, and let us add the third harmonic. So, this is the 0 and so now we see that yes, indeed at this point here theta equal to 90 degrees, at this point theta equal to 90 degrees, this third harmonic is pushing the fundamental down. So, if you add the VCM to the 3 phases, all 3 phases, because it is a third harmonic. So, it is symmetrical about the 120 degree. So, all 3 phases, their peaks will go down at theta equal to 90 degrees, A phase, B phase and C phase. Okay. The peak of B phase will also go down exactly at theta equal to 90 and 270 degrees for their own reference. So, we see that the third harmonic, if we add to this waveform, then it is possible to reduce this peak, and so this waveform will be somewhat like this, the resultant waveform. The resultant waveform will be somewhat like this. We will show you the resultant waveform a little later. So, we see that in this circuit, the addition of the third harmonic here, the addition of the VCM as a third harmonic helps us to push the resultant waveform a little bit down from reaching the +1 and -1 at modulation index 1. In fact, this is the reason where we can go a little bit higher than m equal to 1, and with there we can see, we will see the mathematics now. With the help of this third harmonic addition, the modulation index can in fact be extended up to m equal to 1.15. Okay. So, the RMS load voltage without third harmonic, we have seen it before, is m Vd by 2 root 2, that is 0.35 Vd. This is without third harmonic addition, and with third harmonic addition the m value can go to 15% more, and so we can get 0.4 Vd with the addition of third harmonic. So, summarize, m equal to 1, that is the end of sine triangle modulation or sinusoidal PWM, and with the help of the third harmonic we can go up to m equal to 1.15, beyond which we go into over modulation and eventually ending up in square wave mode of operation, where we get the maximum voltage possible from the converter, that is 1.27 times what we get in sinusoidal PWM, but with the penalty of lower frequency harmonics. So, how do we know now what is the exact magnitude of third harmonic we can add? What is the exact magnitude of third harmonic that we should add so as to push or to get the maximum out of the sinusoidal PWM? So, here we see that there are two waveforms. This is the fundamental waveform, and then we also have the third harmonic which we have added, and the red colored waveform is the resultant waveform after adding the third harmonic. So, we can write the equation of this waveform f theta equal to m sin theta plus k sin 3 theta, where m is the amplitude of the fundamental and k is the amplitude of the third harmonic. So, what are we trying to find is find the value of theta where f theta is maximum, and at f theta equal to maximum find the value of k by m. So, we are trying to find out what is the ratio of k by m, so that we will know that given a value of m, how much third harmonic I can inject, so that I will never cross the plus 1. So, our aim is we will not never cross this plus 1 here by adding the third harmonic. So, we are trying to find out the value of k by m. So, the result is already written here. It will happen at k by m equal to 1 by 6, which means 1/6 of the fundamental is what we should add to increase the modulation index to 1.15. Again I must say that the third harmonic that we add is common to all the phases, it is a common mode voltage. Okay. So, let us do the mathematics here. So, f theta is equal to m sin theta plus k sin 3 theta, and our target is to find out where f theta is maximum first. So, if I differentiate it df d theta and equal to 0 and differentiate this expression, which is shown in some few steps, we come to this equation here, m minus n k cos theta plus 12 k cos cube theta. So, if I equate this to 0 and then solve it, we will get cos theta equal to 0 or m minus n k plus 12 k cos square theta equal to 0. So, if cos theta is equal to 0, which means theta equal to 90 degree, and we can see from this waveform that at theta equal to 90 degree, basically we are getting a minimum of the resultant. So, we will not take theta equal to 90 degree. Okay. We will take the other solution m minus n k plus 12 k cos square theta equal to 0, and then we will first solve the value of cos theta and sin theta here, which we will utilize here. We will put it back at theta equal to maximum, the value of f theta, which is m sin theta plus k sin 3 theta, and expanding we get something like this here, and we have already obtained the value of sin theta at theta equal to maximum earlier, and we substitute that value of sin theta here. And so, we get this expression here. Now, this expression we will differentiate once more to find out what value of k will maximize this. So, we will df theta by dk at theta equal to theta max, we will put it 0 and we will differentiate it once more, which is shown here, from which by several steps we get to an equation here like this, which ultimately comes up to be like this, m square by k square minus 3m by k minus 18 equal to 0. Okay. So, this is the expression which gives us the value of k. Okay. So, if you get to this equation, then by solving this equation we see that m by k, is equal to 6, which means k equal to m by 6, right. So, it means that the magnitude of the third harmonic that we add is 1/6 of the magnitude of the fundamental. Okay, that will be taken, and so at k equal to m by 6, the value of sin theta comes out to be theta equal to 60 degree. So, which means that this maximum will happen at theta equal to 60 degree, as you can see in this curve, that at theta equal to 60 degree we see, and also at theta equal to 120 degree, that is here, we see that the resultant waveform is actually maximizing. Okay. Now, what value of this resultant waveform we should have so as to keep us in the linear modulation? Of course, we would like to touch the +1 at this maximum value of the resultant waveform. Okay. So, we would like to have at theta equal to 60 degree f theta equal to 1, because that is the maximum we can get. Okay. So, if we equate f theta equal to 1 at theta equal to 60 degree, then by substituting we find that m equal to 1.154. So, it means that this value, the resultant value here will touch 1. This is what we expect, the resultant value should touch 1 here. This one will touch at 1 when m equal to 1.154. That means, the sine wave is having an amplitude of 1.154. So, we see that the sine wave is now more than 1. In fact, it is 15% more, but with the help of the third harmonic we have made the resultant inside the +1 and -1, because our carrier is inside here. This is where our carrier is. We do not want to go into over modulation, we will always keep ourselves between +1 and -1, but the fundamental is actually more than that. So, earlier we had also said that whatever is the fundamental voltage in the pole voltage appears across the load. So, if we have 15% more in the fundamental in the pole voltage, it will appear across the load. So, therefore, with the help of this third harmonic we are able to get 15% more voltage from the same DC bus into the load. So, that is the whole idea. So, here here we are showing you the two cases, where first one is m equal to 1 and the second case is m equal to 1.15. These are the two cases we are going to see. So, if m equal to 1, we can add 1/6 of the third harmonic, which I have shown. This is the 1/6 of m equal to 1. So, that is about 0.166. So, when we add this to the resultant waveform, you can see is like this, but interestingly you see this value here. This value, the peak of the resultant is less than 1. So, there is something which we are getting additionally. Okay. This is the extra voltage that we are getting by adding the third harmonic. So, if we get this extra voltage, of course, I would like to increase the modulation index further. So, I have increased the modulation index further to 1.15, and now the fundamental voltage is now more than 1 here, and the resultant waveform you see is touching 1 and 1 here. Okay. So, we are basically able to go 1.15 times the modulation index. Again, it is important for you to understand that this is a common mode voltage. At each instant of time, the same voltage is being applied to A phase, B phase and C phase. It is a common mode voltage. So, it will not allow any current to flow from the load neutral to the source or the inverter neutral here. So, let us see some of the simulation waveforms for this addition of the third harmonic. So, at first we will see the pole voltages. So, we have VDC equal to 600 volt, and the fundamental voltage, fundamental pole voltage that we can get with the addition of the third harmonic will be 1.15 times Vd by 2, that is 600 into 0.5 into 0.98, because we have taken in this example m equal to 0.98. So, this is m here. So, m equal to 0.98, and so we get about 338 volt. If there was no third harmonic, then we would not have got this factor here, we would have got 15% less. So, if you see the harmonic spectrum of this pole voltage, we see that the fundamental voltage is 337.8, it is almost like 338 volt, and we see that there is a third harmonic here. This third harmonic is 1/6 of the fundamental, but it is present in the pole voltage, it is present here, this is the third harmonic. But let us see in the line voltage. In the line voltage, which is again the waveform is shown here, we see there is no third harmonic here. The third harmonic in this place, the third harmonic which was earlier present here, the third harmonic has vanished in the line voltage, which is what we desire. We do not want the third harmonic to come across the load. So, with this VDC at 600 volt, the fundamental line voltage is √3 times what we obtained from the pole voltage, and will be close to 585 volt, and so there is no third harmonics in the line voltage. And what will happen in the phase voltage? We see that in the phase voltage, the phase voltage magnitude, the fundamental phase voltage magnitude is same as the pole voltage magnitude. You see here the fundamental phase voltage is again 338 volt here, but since the line voltage does not contain any third harmonic, it cannot contain any third harmonic because it will always cancel out. So, the phase voltage on the load phase voltage will also not contain any third harmonic, as you can see from the harmonic spectrum. So, in this way we see that by cleverly adding the third harmonic in the modulating waveform, we can get a third harmonic voltage in the pole voltage waveform, but it will disappear in the line voltage and eventually it will disappear in the phase voltage. But what is the benefit? The benefit is that we are getting more fundamental voltage from the same DC bus by adding the third harmonic technique.